Hello, I'm Bob Brown. I'm the author of the textbook used for this class. I believe a recording made in front of a real class is a better experience than a recording made by myself in my office. So most of these videos were recorded during a class that I taught in spring of 2024. Because the recordings were made in a real class, they will contain dates, announcements, and other information not applicable to your specific class. You'll want to ignore that extraneous information. This recording is intended for use by several different class sections with different professors. For that reason, I've removed the class policies from this recording. See your syllabus and the other material for class policies for your specific section. In this class, you'll learn basic principles that will help you succeed in solving information technology problems. You'll learn what to do if a server is thrashing and what thrashing means, what to do when a database with base and index files performs poorly, why redundant storage and backups are both needed for critical data, and what to do when computers on a particular network segment are slow. This course is important for a number of reasons. For example, the boss may come in with an armload of 12 terabyte disks and say, "Build a RAID 5 array for our most critical data." You might say, "Sure, boss, piece of cake." Bzz, wrong answer. You might say, "I don't know, professor said not to do that." And that's a wrong answer too, because you're being hesitant. What you should say is, with such large disks, if one fails, the rebuild time may be longer than the time to the next error, leading to catastrophic failure and loss of data. And then you give a recommendation, and that's going to make you look good for your boss. The boss comes in and says, "The data cleaning job is slowing down the web processor. Spin up a new VM." And you say, "Sure, boss, piece of cake." Bzz, wrong again. You might say, "I don't know, I'm not sure." And again, you're being hesitant. Or you'll say, "Stats show the data cleaning job is thrashing. A new VM on the same hardware will make it worse. I recommend," and you tell the boss how to fix it. Boss comes in and says, "We stored passwords in plain text. That's bad. We need to encrypt them with something like the advanced encryption standard." And you say, "Sure, boss, piece of cake." You already can anticipate the bzzzt. Or you could say, "I don't know. I think there's a reason not to do that." Bzzzt. Or you can say, "Encrypting won't help because the encryption key will have to be accessible to the server." And then you give a recommendation and save the day. Your syllabus is in printable and electronic format. It's in the Start Here area of the D2L section for this course. That's where to look for specific class policies. I mentioned that I was the author of the textbook. The textbook is Computing Concepts for Information Technology: How Computers Really Work. This book is free in PDF form in Desire to Learn. If you prefer a different format, you can buy a print or Kindle copy from Amazon. You can buy an EPUB from Google Play or Apple Books. Any bookstore can order a print copy for you. To find these, search Computing Concepts Bob Brown, and you'll find exactly what you need. But it's important to remember that you do not have to buy these. The PDF that is in Desire to Learn contains exactly the same pages that are in the print copy. Please read the foreword and the preface of the book. The foreword by Dr. Becky Rutherford tells you why this book is important, and the preface by the author, that would be me, tells you some of the things I considered when writing the book. I've been asked whether to study the slides or the textbook. Well, the textbook contains material that's not in the slides, but the slides contain material that's not in the textbook. The lectures explain the slides, but they also add material that may not be in either the slides or the textbook. So you need all three. Do the reading. Do that first. Then listen to the lecture videos. Finally, make notes on the slides and use those notes to study. So you're university students, and as university students, we have some expectations of you. One of them is critical thinking. You're going to analyze a situation, impose order on it, and extract facts and probabilities. You're going to do a little bit of synthesis. Imposing order, you're going to do a fair amount of writing for this course. Writing is good for you because when you're out in the world in your job, the most important ideas you have will be communicated in writing. You do not stand in front of the board of directors and say, I need $10 million for a new computer system. You produce a report that explains the what's, whys, and wherefores. And if it's not persuasive, doesn't look like it was written by somebody with a university education, it's probably not going to get you anywhere. We expect work outside this class. You should assume about 2 hours of outside work for each class hour. For this class, that's about 7.5 hours a week. 2.5 hours in class are working with desire to learn, and 5 hours outside, so about 1 full class day per week, and that's why taking 5 of these makes you a full-time student. Here's a student rating. This was from me, and the student rated me poor. If you look closely, it says textbook use, barely cracked it open. Grade received, D-. The moral of this is that you're going to have to study to earn a satisfactory grade. So what do you have to do to succeed in this class? Read the syllabus, read the textbook, use the SQ3R survey question read recite review method, which I'll talk about some more in just a minute. Come to class if you are in a classroom section and pay attention. If you are in an online section, engage with the class. Take notes. A couple of professors from UCLA and Princeton did a study showing that the pen is mightier than the laptop. Information that you record in handwriting sticks with you better than information you record with typing. Do the homework. The homework is there for you to practice. And we'll see in a video in a few minutes why practicing what you have learned is important. And allow enough time. I'll talk about that a little bit more in just a few minutes. But more bad grades come from procrastination than any other cause. So SQ3R, survey. Skim the assigned readings, look at the headings, look at the diagrams, and get an idea where the author is taking you. Question. Try to turn the main ideas that you got from surveying the assigned reading into questions. Read, do what it says, and add more questions. Do not limit your questions to the initial survey. Recite. Go back and answer the questions you set for yourself. Refer back to the book as necessary. And then review, work through the problems, any end of chapter questions, and any exercises there might be. One of the most important things you can do in any course, not just this one, is keep track of the due dates. Some professors, including me, do not allow late work. You'll get an electronic syllabus that can be printed out, and it'll look something like what you see on the slide. An important thing to remember is that you probably won't look at that much more than after the first week of class. So get those important dates into your own gear. D2L will help you keep track of dates if you log in every day, but you'll probably be better off if you copy the key dates from the syllabus into your own calendar app on your own device. So what are the objectives of this course? What are we trying to do? We're trying to develop a mental model of computing, a way of thinking about computing, of trying to recognize and use computer terminology. Some of you have been using computers since you were old enough to hold one, so there's probably some difference in level in this class. That's okay. We're going to level everything out as we go along. You will manipulate binary numbers. If you haven't taken discrete math or a similar course, stop putting it off. You need to get that behind you. You'll learn to describe the characteristics of digital logic. You'll learn to describe the von Neumann computer architecture. You'll learn to evaluate computer hardware and software systems to describe the functions of the operating system. There are detailed objectives in your syllabus. So those are the objectives. What about your goal? Your goal is to master this material, to master it so well that you can use it in your profession after you graduate. Your professor's job is to help you do that. Another job for the professor is measuring your mastery, and that means grades. Grades are not the objective of this class. They're a measure of the objectives, a measure of how well you achieved the objectives of the course. Take care of the mastery, and the grades will take care of themselves. I did a little experiment a couple of years ago and looked at when people submit homework. About 5% of them submit homework 1 to 2 days before the deadline. These are the people who consistently earn grades of A. 10%, 3 to 24 hours before the deadline, so the same day but with plenty of time. 10%, 1 to 2 hours before the deadline. 65% of students submitted homework less than 1 hour before the deadline, and another 10% either did nothing at all or sent emails in distress saying that, I missed the deadline, can you help me? These are where the unsatisfactory grades come from. I mentioned a minute ago that more unsatisfactory grades come from procrastination than from any other cause. Please don't let that happen to you. So let's talk about the homework just a little bit more. The professor knows the answers, at least usually. I've messed up in the past, but not very often. The purpose of the homework is to practice what you've learned and then to show the professor that you have learned it. The purpose is not to give the professor an answer. The professor already knows the answer. What that means to you is that cut and paste homework will not do and might get you a penalty for academic misconduct, which would be a bad thing. Be sure you understand the policies of your particular course section regarding the use of artificial intelligence and large language models. A misunderstanding there could result in a penalty for academic misconduct. I recommend that you do your own writing even if AI use is allowed. Large language models can have what researchers call hallucinations and produce wrong answers. Besides, you're going to need to learn to write persuasively on your own. Many of the assignments contain short writing exercises, a paragraph or a few paragraphs. Nearly all of the important ideas you'll have in your career will be communicated in writing, so learning to write is important. Use the assignments to practice and do the best job you can. There are several quizzes during the term. Quizzes will be administered using D2L. They're closed book, closed notes, and closed Google. The whole purpose of the quizzes is to encourage you to study as the term goes along. If instead of doing that, you simply look up the answers during the quiz, well, you haven't accomplished anything. Read the assigned material before class, because if you don't, you're never going to read it at all. In class, you should be mostly listening. Make short notes on paper of anything that you think is important, especially if it's not on the material that the professor has given to you. I mentioned the pen being mightier than the keyboard a little bit earlier. Merge your notes onto the slides the following day. Let that stuff simmer in your brain overnight, and then merge the notes onto the slides. Each class day, review the slides and notes from the class 1 week ago. Let's watch a video prepared by me, the textbook author, in which I tell you about the advice I gave to my students. Here's a link to the video. You can Use the link to watch it again and again, and I encourage you to watch it more than one time during this semester.
Hello, I'm Bob Brown. I'm retired, but I taught at Southern Polytechnic in Kennesaw State for more than 20 years. I used to give my students some advice on best practices for studying, and some of them found that advice helpful. I've made this short video with the hope that it will help others. If you've developed an effective regimen for studying, keep it up. If not, perhaps these best practices will help you. Herbert A. Simon was one of the founders of cognitive science. He was a Nobel laureate who held joint appointments in psychology and computer science at Carnegie Mellon University. Here's what Dr. Simon had to say about learning. Learning results from what the student does and thinks, and only from what the student does and thinks. The teacher can advance learning only by influencing what the student does to learn. In other words, your professors can help you and guide you, but learning is entirely up to you. What can you do to enhance your learning? Interacting with the material multiple times is a key technique. If you remember one thing about these best practices, remember reuse of information. Psychologists call this rehearsal. The goal of studying is to move information from your short-term memory to your long-term memory. To do that, you need to use the material at least 4 times with increasing time between exposures. That means cramming doesn't work. You have to space out your studying. Doing that will make you less stressed, too. Simply glancing at the material doesn't work. You must actually use and think about it, relating new information to what you already know to form associative cues, which is why psychologists call this rehearsal. The following information about learning is necessarily highly simplified. The purpose is to explain why you should do these things, and not to be a study of memory models. Let's look at something called the Atkinson-Shiffrin memory model. The model was proposed in 1968 by, as you might expect, Atkinson and Shiffrin, and changed and enhanced for several years afterward. There are more recent theories of memory, and not all psychologists agree about how this works. Even so, this model can help us understand what we need to do to learn effectively. We get a huge amount of input from our senses. For most of us, most of the input comes through our eyes and ears. We don't retain all of it. In fact, most of it is lost immediately. The sensory process in our brains filters in those inputs that have our attention and discards the rest. So if you're reading a compelling text message in class, what the professor is saying at the time is lost. Those sensory inputs which had our attention are committed to short-term memory. To move information from short-term memory to long-term memory requires rehearsal, that is, reusing the information. The capacity of long-term memory seems to be unbounded. Information is returned to short-term memory for use through associative cues, such as an exam or quiz question, or another situation that requires information that we've learned previously. Onward to the best practices. Attend and engage with your classes. Your classes may be face-to-face or online. It doesn't matter. You must keep up with the pace of the class. In fact, asynchronous online classes are harder than classes with established meeting times because they require more self-discipline. In any setting, whether online or face-to-face, you'll have more and better interactions with your professors and fellow students if you're present and engaged. Attending class is not a decision to make, it's something that you need to do. Do the homework. Professors do not assign homework to get the answers. In nearly every case, the professor already knows the answers. Yes, I've made mistakes and assigned problems I didn't know the answers to, but not very often. The purposes of homework are to let you practice the things you're learning and to demonstrate that you know the material. While you're working on the homework, analyze what the professor expects you to learn from each part of the assignment and be sure you're focused on the objective. Is it for proficiency practice, concept formation, to develop the ability to combine ideas, and so on? And remember, you're likely to find similar material on the exams, so do the homework. Find a quiet place and time to study and make studying a daily habit, like working out or practicing music. Studying should be free from distractions. That means put away your phone. Music will distract too. That's why they play music in dentists' offices. If you need to mask distracting sounds, try white noise. If you're given a reading assignment, do it before class and take notes of the important points. Yes, the professor is going to tell you most of it in class or present notes online, but usually the author of the material and the professor are different people. so you get 2 points of view on the same material, and if you're engaged, you get reuse. Don't promise yourself that you'll read it later, because mostly that doesn't happen. In class, listen instead of messing around with your gear. You may have convinced yourself that you can multitask and still absorb the material. If so, you'd be wrong. A study at Bryan College showed that multitasking during cognitive tasks lowers IQ by 15 points. I don't know about you, but I don't have 15 points to spare. If something you read or something the professor says is unclear, ask. If you have a question about something, probably so do others. Professors appreciate thoughtful questions. Asking helps you, helps the professor, and helps your classmates. If you have a question about the material from the reading, hold it until the class reaches that part of the material so that you can ask it in context. In reading, or if the professor says something that sounds important, especially if it's not already in the class material, or if the professor repeats it, you should probably jot it down on paper. Why paper? Professors Pam Mueller at Princeton and Daniel Oppenheimer at UCLA did a study that showed that taking notes on paper is more effective for learning than using a laptop. On the day after class, merge your reading notes and the class notes onto the printed slides or class material. The first time I told a class that, some people just got irate and asked, why should we do extra work when we could just take notes on the slides? First, if you bring printed notes to class, you'll find them a distraction from what the professor is saying. Second, think about what you're trying to do. You're trying to move information from short-term memory into long-term memory, and what does that is reuse of the information spaced out in time. So when you take those notes from the previous day and copy them onto the slides or printed material, you've reused the information. You've done some of that work that it takes to move information from short-term memory to long-term memory. Each class day, review the class material and your notes from the class 1 week ago and review the assigned reading. That spaces out exposure even further and gives you another round of reuse for moving things from short-term memory to long-term memory. After you get back each graded assignment, homework, or test, look at the work you missed to be sure you understand the answer that was expected, and ask yourself what was lacking in your studying regimen that made you miss that item. If necessary, adjust your studying regimen. If you follow these best practices, engage with your classes, do the homework, study at the same time and in a distraction-free place, read the assigned material before class, listen in class, ask questions, take notes in class, merge the notes onto the material the professor provides, study your merged notes a week later, and learn from the graded material, you've gotten 4 or maybe 5 licks at the material without really doing very much work other than what you should have been doing anyway. By dividing it up into chunks, you stand a much better chance of remembering it at least until the exam, and maybe even remembering it long enough to use in your career. This works in every class you take. If you do this, you'll learn more, and as a side benefit, maybe make better grades.
Let's get started on the meat of the course. Let's think about a mental model of a car. Everyone here either drives or has ridden around in somebody's car. And particularly if you drive, you've developed a mental model of that automobile, so you know about engines and electrical systems and steering and brakes and all of that stuff. Some of you have had car trouble, and when you had car trouble, you were able to guess what was wrong based on that mental model of the car. You applied the mental model, did some diagnosis, and knew what had to happen to fix the car. How much detail in the mental model of the car? About this much. This is something that you probably would have learned in middle school about internal combustion engines. There's not enough detail there to build an internal combustion engine, but there's enough to understand one. There are several different mental models of a computer. We can have a number of choices. We can think about the physical pieces, the system unit, the monitor, or the keyboard, or we could think about the logical pieces, the CPU, the random access memory, the input, and the output. We could think about the applications. What are the things we're going to do with the computer? We could think about the computer as a storage device. I try not to let paper come into my office because I want things electronically, and then I store them electronically so that I can find them. We might think of a computer as a networking and communications tool. And we would use different mental models for different ways of thinking about a computer. If I'm worrying about storage, I probably don't have to worry about applications, but I might need to worry about how much storage I have and maybe about networking if I'm using storage on a distant computer. Without that well-focused mental model, it's hard to use anything effectively. Technology, and particularly technology involving computing, has advanced very quickly. The good news for us is that the basic ideas have changed very little in half a century. So we're going to learn those basic ideas, and then we're going to relate them to current technology. That's good news for us. So who can benefit? Why do you care? Users of computing systems can understand the capabilities, make informed decisions, improve communication with people like yourselves. The systems analyst conducts surveys, determines feasibility, specifies computer systems. The programmer can create efficient application software by understanding how the computer works. The systems administrator or manager can install, configure, maintain, upgrade computer systems, maximize system availability, optimize performance, and assure system security. Who else? Web designers can optimize customer accessibility. System administration of web servers is important. Selection of appropriate data formats and design of efficient web pages is important. Computers are almost everywhere, and we come in contact with them every day, so almost anyone can benefit. Now, I'm going to tell you about a key tool. One of those tools that we use for developing mental models is this thing called abstraction. Abstraction is removing unnecessary complexity. Unnecessary and unneeded is in bold and underlined because it's a key part of the definition. So we can have different mental models at different levels of abstraction. We'll select different mental models for different purposes. Now listen up. This applies to all of your classes. That business of abstraction, of removing unneeded complexity and developing mental models, is a superpower. If you try it, you'll do better in all of your classes, not just this one. So here's one mental model of computing. It's the input process output, or IPO model. There's nothing in this diagram that looks very much like a computer. What we're focused on in this mental model is transformations. Input, process, and output. Time cards go in, paychecks come out. Test scores go in, grades come out. So we have an input, some defined process, and a desired result. We can think about computing that way, and all of the details about CPU and RAM and gigahertz and all of that stuff is abstracted away. It is not important to this mental model, although it is important to some others. This mental model does include storage because almost no processing takes place without storage these days. Here's another mental model, also an example of abstraction but very different. In this case, it's a mental model of the physical parts of the computer. So I've got communications, storage, keyboards, monitors, disks, speakers. I don't have a printer, but I could put one in there if I needed to, right? Both of these are mental models. They are alike in some ways. Storage is represented explicitly in both places. Input and output is represented in both places. There's lots of detail in one of them, very little detail in the other, but they're both there. There is at least one other similarity. What is it? Processing. We've got our central processing unit with memory and its I/O interface in both places. More detail and a focus on the physical is in the second diagram. In the first diagram, the one on the upper left, we're thinking almost entirely about the logical capabilities of the computing system. The second one, on the lower right, focuses on the detail, the physical part of the computer system. So on the upper left, we have a functional abstraction, and on the lower right, we have a physical abstraction. There are a number of abstraction mechanisms. One of them is pattern recognition. We use pattern recognition both to classify and to generalize. Generalization is identifying something as a subtype. For example, a car is a type of vehicle. Generalization is transitive, but classification is not. System components can be irreducible, and the example is a bolt. A bolt can't be further reduced. Or they can be subsystems that can be decomposed and broken down into simpler and simpler abstractions. Decomposition is the division of a system into its components and linkages. We can do functional decomposition, that is, decomposed by function, and you saw that in the input-output process model. We can do physical decomposition, decomposed by physical units, and you saw that in the physical abstraction diagram. We can also do hierarchical decomposition, decompose until all components are irreducible. We don't do that very often. Let's see some more examples of abstraction. On the left is an abstraction of the von Neumann computer architecture, and we're going to look at that in a lot more detail next time. This thing, the bullet shape with a couple of inputs and an output, is the diagram symbol for an AND gate. And we'll talk about AND gates when we get to digital logic. At the bottom right is a circuit diagram made out of AND gates and two other types of gates. This particular diagram is a full adder, but we don't need to worry about its function just yet. What's important here is that instead of a handful of transistors and power supplies, we have abstract symbols for the kinds of processing that this circuit does. Here's our adder again. It's been turned on its side, and I drew a box around it, but the inputs and outputs extend outside the box. I can abstract further by labeling the box full adder, labeling the outputs, and forgetting about the circuitry that's inside. Now I simply understand that this box performs binary addition. When I've done that, I can make a 4-bit ripple carry adder, one that adds 4 bits of binary digits by daisy chaining those full adders together. You can see how powerful a tool abstraction can be in understanding what's going on with a computer system or anything that's relatively complex. We're well into the 21st century, almost a quarter of the way in, and digital computers are everywhere. You almost certainly have one with you, although you might call it a phone. You're more likely to be reading this book on a digital device than on paper. There are huge data centers with thousands of pizza box-sized computers. They run things like Google and Amazon. There are still mainframe computers in about 2/3 of the Fortune 100 businesses. There are supercomputers used for modeling and other tasks that require intensive computation, embedded computers in things like microwave ovens, and all of them are interconnected. An electronic digital computer is a machine. It has mechanisms for receiving input, for processing and storage information, and for producing and communicating results. You'll find computers in all kinds of specialized devices, but the computer itself is one of the most general-purpose machines ever devised. The more general a technology is, the more varied uses to which it will be put. We use computers for everything from preparing tax returns and processing them to landing airplanes, generating medical images, and displaying pictures of cats. All computers consist of 3 things: Hardware, software, and data. Hardware executes the instructions, provides the mechanism for input and output, and provides for temporary and long-term storage. Software, that's computer programs in the language of the machine, binary numbers, zeros and ones. Data are the representations of facts, measurements, observations in a form that can be used by computers. Now, saying every computer has all three of these things is a very bold statement. Every is a bold word. How about the computer that costs 4 cents and goes inside one of those annoying greeting cards that makes noise when you open it up? Well, there's hardware, a little chip in there. Something happens to make that chip go. Data, yep, it sings happy birthday to you in a tin voice. So even for the simplest computer I can think of, I've got hardware, software, and that song that the computer sings is the data. The Internal Revenue Service, a big computer somewhere in suburban Washington, D.C. maybe. Hardware, software, and data. Hardware executes the instructions, and you'll know in a fair amount of detail about what an instruction is, and the mechanism for doing input and output, and the mechanism for doing long-term and temporary storage. Software, computer programs, and by the time a program is actually executed on the computer, it's in binary form in the language of the machine. And we'll talk about that as we go along. Data, representations of facts, measurements, observations in a form that is binary numbers that can be used by the machine. All computer systems, no matter how complex, consist of at least the following. All computers have at least one central processing unit, some sort of memory to hold programs and data, some sort of input and output mechanism, and some mechanism for long-term storage. Now let me say, if you bought a microwave oven anytime since about 1980, if you have an older one, please pitch it. It's going to microwave you. If you bought a microwave oven anytime since about 1980, it has a computer in it to control the microwave oven. That computer replaces all of the springs, switches, and gears that used to be in microwave ovens before computers and embedded computing. So does your microwave oven have these 4 things? Yes, indeed. There will be a CPU in there. There will be memory, because the program is still there when you turn it back on. Memory for data? Sure. How long do I want to nuke this thing in order to set off all the fire alarms in the building? Every now and then somebody comes in with a bag of popcorn, they punch up 27 minutes, and they head for the men's room or something. I don't know where they go, but what happens is the fire alarm goes off because they've burned down an entire bag of popcorn. Input and output, do we have I/O in the microwave oven? Sure, beep, 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 27 minutes. Output, we've got a little countdown timer going on that tells us how many seconds are left. But more important than that, we've got output controlling the magnetron that's generating those microwaves. So we have some internal output, as it were. Even that simple embedded computing system has all of those things. A computing system is more than just hardware and software. The hardware is necessary. There are several layers of software, at the very least an operating system and application software, communications facilities, data, and all of this has a purpose of solving specific problems or performing specific functions. We might have a problem that is mapping the human genome or a problem that is playing solitaire, but we're always solving some specific problem. Virtual, according to the American Heritage Dictionary, says existing in result or essence or effect, but not in actual fact, form, or name. Brown's definition is a little simpler. You can see it, but it's not really there. American Heritage then says created, simulated, or carried on by means of a computer or computer network. There are a number of examples of virtualization in computing. We'll talk about virtual memory. We're going to talk about a virtual machine in just a few minutes. Then there's that Java virtual machine that lets Java work. Everybody has taken a programming course before you got here, so you already know about the job of virtual machines. A virtual machine is a combination of hardware and software that presents specific interfaces to the application software, and those specific interfaces are not supported by the hardware alone. The hardware and software together define a virtual machine. So hardware and software, there's a computer under my desk, it's running Windows 11, and I have a Windows 11 virtual machine. I could come in with a handful of CDs, format the disks. I can have a Linux virtual machine on the same hardware. Let's look a little bit more closely. Down at the bottom, level 0, is the physical machine. We're going to call it M sub 0, and it has a machine language L sub 0. That machine language might be microcode or built-in firmware. At level 1, we have machine instructions. This is where the operating system lives. So I have a virtual machine, M sub 1, this is the machine that runs the operating system, and a machine language L sub 1 machine instructions. One level up, the language's operating system calls, mixed in with those machine instructions, and most applications are at this level. I can go further to another level and have something that is Java bytecode, an application running on an operating system that in turn interprets code generated by a Java compiler. So I can layer things as deeply as I need to accomplish what I'm trying to accomplish. I told you you'd see this again. This is a schematic description of the von Neumann computer architecture. We'll talk about John von Neumann and why this is important quite a lot as we go along. You're going to see this diagram 27 times this semester. I made up 27, but you're going to see it in the double digits probably. What does it mean when the professor shows you the same thing half a dozen or a dozen times? It's important. And once you realize something is important, what do you infer from that? Well, you should know it's going to be on the exam, but you should also know you're going to use it in real life. Okay, so this is a diagram, a schematic diagram of the von Neumann computer architecture. This is the central processing unit, or CPU, there in the middle, that rounded thing that's gray and labeled central processing unit. The central processing unit itself has several components: a control unit, an arithmetic logic unit, and registers. Registers are small, fast memory that hold data that's being used at that moment by the CPU. The fat arrow on the diagram says I can send more than one bit of data at the same time across this path. And the double-ended fat arrow says it's bidirectional. I can move data in both directions. So we see that the central processing unit is connected to memory on the right and to the outside world through input and output on the left. This basic architecture is left over from the 1940s, so it's 80 years old and is still the way computers are designed in the 21st century. The arithmetic and logic unit performs, as you might expect, arithmetic operations on data and logical operations on data. It can also be used to transfer data within the CPU and from the CPU to the input and output system. The control unit controls the processing of instructions. The arithmetic logic unit is the thing that does the processing. The control unit controls the processing. Part of the control unit is this thing called the program counter. We'll see the importance of the program counter a little bit later, but we'll talk about it as we go along. The program counter holds the address of the next instruction. Let me say that again. The program counter holds the address of the next instruction. This is absolutely, positively going to be on exams. The program counter holds the address of the next instruction. Experience says about a third of you are going to get that right. Please do better than a third of you. Registers, small, fast storage that's part of the CPU. The number of registers ranges from a few to as many as 128 or 256. There are not thousands of them. The size of a register is generally the word size of the computer architecture. So a 64-bit computer is likely to have 64-bit registers. There are registers that are used for special purposes. For example, a 64-bit computer might have 128-bit floating point registers. The interface unit is responsible for moving data among the parts of the computers. A big part of that interface unit is something called a bus. A bus is a collection of wires or electrical conductors or traces on a wiring board or within a chip. In every case, it's a collection of electrical conductors, and the job of that bus is to carry data and sometimes power among the parts of the computer. Now, I said data, but it can also carry addresses, status, and control signals. Memory, also known as RAM or random access memory, main memory, or primary storage, is where computers and data live while the computer is running. So as the slide says, memory holds instructions, and those instructions are in machine language, and the data for the programs that are running at that moment. The stored program concept, that's something else invented by John von Neumann in the 1940s, and this was a great aha experience. Von Neumann said, if I represent a program as a series of binary numbers instead of a collection of wires on a plug board, I can store those binary numbers in the same memory that holds the data. Instead of having to rewire the computer when I have a new problem, all I have to do is load a new program into the computer's memory. That's obvious to us, but it was a great aha experience about 1946 or 1947. The program counter, which holds the address of the next instruction, is what keeps track of those instructions in memory. So the last thing I want to say today is I want to tell you about a book by John McCormack, 9 Algorithms That Changed the Future. Now, McCormack's definition of algorithm is a little bit different and a lot broader than mine. But search engine indexing and the PageRank algorithm that started Google, public key cryptography, which we'll talk about toward the end of the semester, forward error correction, pattern recognition, data compression, databases, and digital signatures. This book is in the Sturgis Library on the Kennesaw campus, but you can request that it be sent to the Johnson Library using Gill Express, and then you can check it out and read it. I would add to McCormack's list large language models. Large language models did not exist when McCormack wrote his book, but they are now extremely important. So that's everything that I have to say for the introductory part of this course. I look forward to riding along with you for the remainder of the semester. I hope you will spend some time with these recorded lectures, and I hope they help you.